Ever seen a spider robot in action? Well, in this series we are crafting our very own. Using materials that are easy to find, we are crafting a DIY spider robot. And I'm inviting you to join me on this adventure. Now, a small confession. I'm learning as I go. Some challenges still puzzle me. And the beauty of this series is that we'll tackle them together, step by step. If you are new here, I suggest starting from the beginning to get a full experience. Throughout this series, I'll break down each part of the project, ensuring you can follow along with ease and maybe even kickstart your own robotic creation. I aim to keep these sessions short and to the point. However, if anything feels a bit rushed or unclear, don't worry, I've provided supplementary documentation and Jupyter notebooks to help reinforce and expand on what I cover. Remember, it's about the journey and understanding, not the pace. For those interested in the tools, you'll find all the details in the description below. Join me and let's embark on this exciting DIY voyage together. Today's enchanting adventure begins with exploring the secrets of inverse kinematics, where we'll learn how our spider robot will move its legs to traverse its surroundings gracefully. In this tutorial, we'll learn how to write a SpiderLeg class to perform inverse kinematics calculations for a spider robot leg. Inverse kinematics is a method used in robotics to calculate the joint angles required to achieve a specific target position in the workspace. The opposite of inverse kinematics is forward kinematics, which calculates the position of the end effector, for example, the tip of a robot arm or leg, given the joint angles. In the case of our spider robot leg, we have three joints: the coxa, hip, femur, thigh, and tibia, shin. Each joint has an associated angle, which we'll call θ1, θ2, and θ3. Our goal is to determine the values of these angles that will place the leg's end effector, the foot, at a desired target position, x, y, z. However, this is just scratching the surface of the spider leg's complex kinematics. For a more in-depth understanding and to see the intricate interplay of these angles and segments, I highly encourage you to visit my detailed tutorial on GitHub, where I break down the concepts further and provide a comprehensive guide to the sophisticated world of inverse kinematics. In the example above, we have defined a simplified spider leg class that represents a single leg of a spider robot. The class includes the following elements. The init method initializes the class with a name, segment lengths, coxa, femur, and tibia, and initial joint angles, θ1, θ2, and θ3. The forward kinematics method is called to calculate the initial joint positions. The inverse kinematics method is a placeholder for the actual implementation of inverse kinematics calculations. When given a target position, this method should compute the joint angles θ1, θ2, and θ3 required to reach the target. The forward kinematics method is a placeholder for the actual implementation of forward kinematics calculations. When given a set of joint angles, θ1, θ2, and θ3, this method should calculate the resulting end effector, foot, position in the 3D space. This simplified structure provides a foundation for implementing the inverse and forward kinematics algorithms. You can extend the class by adding more functionality, such as methods to control the servos, update the joint angles, or visualize the leg movement. Next, let's revisit fundamental trigonometric functions. Sine, cosine, and tangent are crucial for understanding the angles and sides of right-angled triangles. We also dissect the cosine rule, a pivotal principle that extends beyond right-angled triangles, helping us determine unknown sides and angles. These concepts are not just theoretical, they're the building blocks for calculating precise movements of our spider leg model. While these explanations provide a snapshot of the mathematical intricacies involved, I invite you to join me on GitHub again for a comprehensive breakdown. There, I unpack these concepts further, ensuring you have a robust foundation to tackle the complexities of inverse kinematics. I apologize for the lengthy introduction, but it's essential for understanding what's to come. Now let's move on to the actual calculation process and dive into the practical side of inverse kinematics. Thank you for your patience. Let's get started. Now let's begin the process by calculating the first angle, θ1, which determines the leg's horizontal orientation. To do this, we can imagine a right-angled triangle formed by the x and y axis and the coxa extension. We need to find the angle between the x-axis and the coxa, which we can call θ1. To determine the actual angle, θ1, we use the arctangent function, often abbreviated as atan, This mathematical tool calculates the angle when you know the ratio of the opposite side's length to the adjacent side's length in a right-angled triangle. Essentially, it helps us figure out the steepness or incline angle based on the triangle's dimensions. So, in our right-angled triangle with legs x and y, the tan y over x gives the angle theta 1 between the x-axis and the coxa. This calculation gives us the horizontal orientation of the leg, which is an essential first step in determining the joint angles for inverse kinematics. Next, we'll calculate intermediate values needed for determining theta 2 and theta 3. We'll use the sine and cosine functions to find the lengths xa and ya, which are the projections of the coxa segment along the x and y axes. Now we'll find xb and yb, which are the remaining distances along the x and y axis from the coxa segment to the target position. To find p, we can use the following relationship based on the cosine function for a right-angled triangle. In our case, the adjacent side is xb, and the hypotenuse is p. Rearranging the equation, we get, which we translate to Python code that calculates the hypotenuse p, which is the horizontal distance from the end of the coxa to the target point in the horizontal plane. G is the absolute value of the z coordinate of the target position. It represents the vertical distance between the coxa-femur joint and the target position along the z-axis. We can imagine a right-angled triangle with P as the base, adjacent side, G as the height, opposite side, and H as the hypotenuse. In this triangle, the angle between the base, P, and the height, G, is a right angle, 90 degrees. The Pythagorean theorem states that in a right-angled triangle, the square of the length of the hypotenuse, the side opposite the right angle, is equal to the sum of the squares of the lengths of the other two sides. To find the length of h, we can take the square root of both sides of the equation. Next, we'll use the arcsine asin function, which is the inverse of the sine function, to find the angle phi 3. In a right-angled triangle with legs g and h, the arcsine g over h gives the angle between the side opposite the angle and the hypotenuse. Now, we'll apply the cosine rule to find the angles phi 1 and phi 2. The cosine rule is a formula that relates the lengths of the sides of a triangle to the cosine of one of its angles. We'll rearrange the formula to find the cosine of angle C. With the phi 1, phi 2, and phi 3 values calculated, we can now determine theta 2 and theta 3 based on these values and the sine of z. When the leg is lifted above the coxa, z is larger than 0. In this case, the target position is above the coxa-femur joint along the z-axis. To reach this position, the leg needs to bend backward. To calculate the correct value of theta 2, we need to consider both phi 1 and phi 3. We add them together. When the leg is lowered below the coxa, z is less than 0. In this case, the target position is below the coxa-femur joint along the z-axis. To calculate the correct value of theta 2, we need to consider the effect of phi 3. Finally, we'll calculate theta 3 as the sum of phi 1 and phi 2. With the angles theta 1, theta 2, and theta 3 calculated, we can update the joint angles. To summarize, we've used trigonometric functions such as sine, cosine, and tangent, as well as the cosine rule, to calculate the joint angles required for our SpiderLeg model to reach a specific target position. By understanding the relationships between the lengths and angles in right-angled triangles, we've been able to apply these principles to a more complex three-dimensional problem. It's important to note that the actual structure and movement of a spider leg in nature are far more complex than our simplified representation. In this tutorial, we are using a basic mechanical model with 3 segments and 3 joint angles to help us understand the fundamental concepts of leg movement and inverse kinematics. Keep in mind that real spider legs have more intricate joint structures, muscle systems, and movement patterns, and our model serves as an approximation for educational purposes. Please also note that the approach presented in this tutorial is a simplified, you could say naive method for solving inverse kinematics. In robotics and more advanced applications, there are more sophisticated methods used for inverse and forward kinematics, such as the Denovet-Hartenberg method, the Jacobian method, or the cyclic coordinate descent method. These methods offer more accurate and efficient ways to solve inverse kinematics, especially for more complex robotic systems. However, for the purpose of this tutorial and for a better understanding of the basic concepts, I have chosen a simplified approach. If you want to learn more about those advanced topics, strongly advise you to follow up with lectures of Angela Soudman. You will find links to her lectures in the video description. And there you have it. I really enjoyed creating this video for you, and I hope it has helped you understand the workings of a simplified SpiderLeg model and the trigonometry behind it. I'm always looking forward to hearing your thoughts, so if you found this video helpful or have any suggestions for what you'd like me to cover next, please leave a comment below. Your feedback will help me create better content for you in the future. Remember to like this video, share it with your friends, and subscribe to my channel for more educational content like this. Thanks for watching, and until next time, happy learning.